And even to make the efficiency of the class B amplifiers to improve, you can even have a transformer. So as we have did it in the class A amplifiers, you have two transformers, one at the input side, one at the output side. Input transformer will isolate the input and the amplifier. The output transformer will ensure that the maximum power is transferred from the collector to your load. See, we use transformer to boost the coupling efficiency of your device. Okay, that is the reason why we are going for transformers. Transformers always boost your efficiency. Only drawback is they are bulky, so you cannot make your circuit compact whenever you are going to use transformers. Okay, so that is the only drawback of using your transformers. So the waveforms are shown here. You can see that the input and output waveforms are 180 degree out of phase, because in a common emitter amplifier, the 180 degree phase shift will always be there. Okay, and the power output is given by Vrms into Irms. So Vrms is Vm by root 2, Irms is Im by root 2, and so it is Im Vm by 2. It is Im by 2 into Vm. So Vm is the maximum value. Maximum value is varying from Vcc to V minimum. So the maximum value, the maximum swing can change from VCC to V minimum. That is the maximum value your VM can take. So it is Im by 2 into VCC minus V minimum. So that is going to be your output power. Output power is AC power. And input power is the current to IC into VCC. It is 2 into IDC into VCC. Okay, so it is DC current, and I told this DC current is average value. This average value is given by Im by pi. So when you add all the values of a sine wave and divide by the number of values, you get the average value to be Im by pi. And so it is 2 into DC into IDC into VCC, 2 into Im by pi into VCC. Okay, this this 2 is coming because we are going to use 2 transistors in our system. So next topic is going to be construction. Maybe in that you'll understand. Usually, it is power input is VCC into IC, but here VCC into 2 IC, because I'm going to use 2 transistors. So the current will be additive, and I'm assuming the transistors to be identical. So IC plus IC is going to be 2 IC, and that is going to be the average current. So 2 into Im by pi into VCC. This is the input power. So efficiency, output power by input power. So output power is Im by 2 into VCC minus Vmin. This input power is 2 Im by pi into VCC. So if you substitute, you get pi by 4 into Vm by VCC. Okay, pi by 4 into Vm by VCC, or pi by 4 into 1 minus V minimum by VCC. V minimum is going to be 0. Or it is VCE, which is very, very small, and VCC, it is going to be the maximum value. So if you put V minimum equal to 0, you will get pi by 4. Pi is 3.14. So 3.14 by 4, if you calculate, you will get the answer to be 78.5%. So assuming V minimum is 0, usually V minimum will be 0.1 or 0.2, very, very small when you compare to VCC. So when you substitute that, you get the maximum possible efficiency for class B amplifier is 78.5%. Whereas it is only 50% for class A. So you have seen a 28.5% jump in the efficiency just because during negative half cycle, the transistor is not conducting, so you don't have any power loss. That power loss, which is not happening, is reflecting in the efficiency. So such a large value of efficiency is possible because there is no current excitation in class B during the negative half cycle. Whereas in class A, there is a constant current flowing through the device always, which is going to contribute for your power loss. See, anything power loss and efficiency are related. When power loss is going to be very high, efficiency will be very poor. They are inversely related. So whenever you are able to control the power loss, definitely you will see a significant improvement in the efficiency. That is evident in class B amplifier. In class A, theoretically, for a series fed, it is 25%. When you are going to use transformer, it is going to become 50%. But this 50 is becoming 78.5 when I am going to use class B operator.